thoughts on P-adic number theory. These lectures are based on my book called Introduction to P-adic Analytic Number Theory, which I think was published by the American Math Society, Plum Press, I think, or something like that. And so I'm going to try and summarize the contents of that book through 5 lectures, and I will try to not go too fast. Surprisingly, today is the 60th anniversary of Martin Luther King's March for Civil Rights in America, August 28, 1963, during which I was alive. I was just a child at the time, and I was wondering what this was all about. And it's about civil rights, about the equality of all human beings to live peacefully on this planet. And I hope that education, in the true sense of the word, will go a long way to achieve this remarkable dream of Martin Luther King. So with that said, let me begin by talking about an important analogy between numbers and functions that seems to have energized the development of P-adic analytic number theory. 20th century number theory took a quantum leap forward by noticing that there's a profound analogy between numbers and functions. For instance, by the end of the 19th century, it was known that every meromorphic function had a Laurent expansion of the form summation a sub n z minus c to the n. So we know that certain reasonably well-behaved functions have what are often called Laurent expansions, or maybe, if you like, Taylor expansions of sorts, where you expand the function about a particular point. Motivated by this analogy, Kurt Hensel in 1897 discovered that every rational number has a P-adic expansion. So there's this kind of analogy. Even if you don't understand the statement, hopefully by the end of today's talk, you will be able to understand what I'm trying to say here. This analogy between meromorphic functions and numbers and P-adic expansions is essentially at the heart of what I would like to discuss. So points in the complex plane can be viewed as prime numbers of a certain ring. And so in this analogy seemed to go beyond mere poetry. And that's the amazing thing. So in a nutshell, this is what I would like to achieve by the end of the 5 lectures, an understanding of what I'm trying to say. What is this analogy between numbers and functions? So this question has to begin with trying to understand what is a prime number. And you will see that this is not a simple question to answer as we think it might be. Of course, so let's begin with a naive preliminary definition that most of you are familiar with. A prime number is a natural number greater than 1, which has no proper divisor. And here, when we say proper, we mean non-trivial. And since every number is divisible by 1 in itself, so those are trivial divisors. And if those are the only divisors, we say it's a prime number. So this is the definition that perhaps everyone has learned in school. But this definition will change by the end of this talk. Prime numbers are important in mathematics because they're the building blocks of all natural numbers and consequently all of mathematics. Isn't that amazing? Just as physics looks to find building blocks of all physical matter, number theory in particular studies prime numbers and their properties to understand the nature of mathematics itself. And we all know mathematics is the foundation of modern civilized life. This interchange through the internet is impossible without mathematics. Euclid was the first to define the notion of a prime number, but strangely, he did not prove the unique factorization theorem, even though he had developed all the tools to prove the theorem. And the unique factorization theorem appears for the first time in print in 1801 in Disquisitiones Arithmeticae, written by Gauss. So this is something that many people do not know. We often attribute the unique factorization theorem to Euclid, but the fact of the matter is he didn't write it down. He didn't even state the theorem. It was first stated in Gauss's Disquisitiones Arithmeticae, which is again perhaps a chapter in the what can be called the philosophy of mathematics, the philosophy of discovery, how does one miss making certain discoveries due to historical accidents or historical movements of thought. So Euclid did discover what's called the division algorithm. So this is the fundamental tool that's needed. Given two natural numbers a and b, we can find natural numbers q and r such that a equals bq plus r, with the remainder r being less than b. I mean, you take a number, natural number a, you divide it by the number b, you get a certain quotient q and a certain remainder r. So this we know from grade school, elementary school. And with this, one can show that there's a well-defined notion of the greatest common divisor of two natural numbers, a and b, and that they're always integers x and y, such that ax plus by is the GCD of a and b. So these two things, on one hand, that you can take any two natural numbers, a and b, or take any integers for that matter, and find integers x and y, such that ax plus by turns out to be the GCD of a and b. This is something that you would do from using the division algorithm. From this particular fact, it's then routine to prove the unique factorization theorem. And the first step is to show if the P is a prime dividing A, B, then it must divide A or B. That is, you can't break up the prime into two non-trivial pieces. So the proof goes like this. Suppose P does not divide B, then P and B have GCD equal to 1. Therefore, by the division algorithm, there are integers x and y, so that px plus by equals 1. Multiplying through by a, we get pxa plus aby equals a. And as p now divides pxa, and p divides ab, therefore p divides ab times y, therefore it has to divide the right-hand side, so p divides a. So that's the proof that if p divides ab, it has to divide one or the other. Now, I keep saying this. These are not to be dismissed as elementary or routine because they are certainly properties of primes, but it still begs the question as what is a prime number? And this is not an easy question. Maybe we can even say to this day, we don't have a comprehensive answer to this question. Certainly, we have many ways of describing prime numbers, but this is not the totality of our knowledge. So with this in place, we can actually prove the unique factorization theorem. And the way it goes is like this. It was given by Gauss. If n is a natural number greater than 1, and it is not a prime number, we can decompose it as a product of two proper divisors. And we can repeat this to each of the divisors. And this cannot go on indefinitely because of the Bell-ordering principle. As you keep on chopping the number down and down, well, they're getting smaller natural numbers. And eventually, it has to come to 1, and therefore, you can't go on indefinitely. Sorry. So each number admits a factorization as a product of prime numbers. And now the question is this a unique factorization? Well, if we had two different factorizations, say, n can be written as P1, P2 to PS with the PI's primes, Q1, Q2 to QT with the QJ's primes, we can also assume that any common prime on both sides can be eliminated. And so we can assume that the P's are different from the Q's. But now we can use the lemma proved earlier. P1 divides the product of the Q's, so must divide at least one of them, and so it can cancel again, and that's a contradiction. So this is basically the proof of the unique factorization theorem. Now, the interesting thing about natural numbers in their study, it seems to have been not only Euclid, but Aryabhata seems to have done quite a bit of work on this. And Aryabhata was also interested in trying to find a formula for the sum of the kth powers of the natural numbers. So if I were to sum 1 to the k plus 2 to the k to n minus 1 to the k, is there a formula for this? This problem appears for the first time in Aryabhata's book called Aryabhatiya, written in the 5th century. But later again, it's discussed by Jacob Bernoulli in 1713. And Aryabhata writes down a general formula for k equals 1, 2, and 3 in his derivation indicates he knew the general pattern. But the general formula first appears in the 1713 work of Ars Conjectandi. That's the book written by Jacob Bernoulli, where the numbers now called Bernoulli numbers are defined via power series. So the power series is you take the function t divided by e to the t minus 1, and you develop it as a power series. And this power series turns out to be summation b sub k to the k over k factorial. And notice that since e to the t minus 1 is a power series with rational coefficients, when you take two rational power series and you take their quotient, the quotient power series is again another power series with rational numbers. So the Bernoulli numbers, b sub k's, are rational numbers. Now, the use of power series in trying to understand the phenomenon of numbers or sequences in general is a common idea in mathematics. So remember now, that's our definition of the series. A general method often used to understand sequences via the method of generating functions. So we can package our sk of n as follows. So if I package my sk of n into a power series, then I can rewrite the power series as summation t to the k over k factorial times summation j to the k j equals 0 to n, and then we can interchange the summation and recognize that the inside sum is simply either tj, and that can be as a geometric series. We sum this, and we can rewrite this sum as a product of two things, either the nt minus 1 divided by t times t over e to the t minus 1, recognizing the fact that t over e to the t minus 1 is this series with Bernoulli numbers. We can put that in here. And then having done so, we find that comparing coefficients of t to the k on both sides gives the following formula. And so the formula is given by this beautiful expression, k plus 1 s sub k of n is summation I equals 0 to k, k plus 1, choose I, b sub I, n to the k plus 1 minus I. Very beautiful formula. And so if you look at your examples, k equals 1, k equals 2, k equals 3, which Aryabhata had actually done, you can see that the formula as for sk of n is a formula with it's a polynomial in n, and the coefficients now have been given meaning. The coefficients are now Bernoulli numbers. And if you write k plus 1 choose I as k plus 1 divided by k plus 1 minus I times k choose I, then you can simplify the formula and get sk of n is equal to summation I equals 0 to k, k choose I, b sub k minus I, n to the I plus 1 over I plus 1. So it's a very beautiful formula, I would say. I don't know how you would see it, but certainly something that I'm sure intrigues every child when they see this formula, that you can actually write down the formula and that it's a polynomial in n. See, that's not obvious. But Aryabhata seemed to have known that it's a polynomial in n because his work shows that. But the significance of the coefficients, perhaps, and how the recursive relations of these coefficients was first highlighted by Bernoulli. So this leads us to the concept of Bernoulli polynomials. We define the nth Bernoulli polynomial as b sub n of x, which is equal to summation k equals 0 to n choose k, b sub k x to the n minus k. It's a polynomial of degree n. And then we can write our formula for sk of n in terms of the special value of the Bernoulli polynomial, 1 over k plus 1, b sub k plus 1 of n minus b sub k plus 1. A very beautiful formula in its own right. The Bernoulli polynomials have the generating function. So just like we wrote down a generating function for the Bernoulli numbers, we can write down a generating function for the Bernoulli polynomials. And t times e to the xt over e to the t minus 1 is summation k equals 0 to infinity bk of x t to the k over k factorial. So this we get as we did before with the other thing. And we can rewrite the expression involving the Bernoulli numbers in the following way: t over 2 plus summation k equals 0 to infinity bk t to the k over k factorial. We can rewrite that as t over 2 plus t over e to the t minus 1. And then notice that the right-hand side is an even function of t, and this allows us to deduce that all the Bernoulli numbers b sub k are 0 whenever k is odd and bigger than or equal to 3. So we have this interesting sequence of numbers just emanating from a very simple question. Find a formula for the sum of the kth powers of the first n minus 1 natural numbers, a question that was asked first by Aryabhatta in the 5th century, and all of a sudden it gives rise to the sequence of Bernoulli numbers, and these Bernoulli numbers are going to play a very important role in the theory of P-adic numbers and P-adic zeta function. So we'll discuss that, but one has to enjoy, perhaps, and savor the depth and profundity of ideas emanating from very simple questions, such as trying to find a formula for the sum of the kth powers of the first n minus 1 natural numbers. Now, let's move forward a bit beyond the Bernoullis and move towards Euler and the zeta function. A fundamental method of research is what can be labeled as reinterpretation, taking a known idea and reframing it in a new way, giving rise to a new perspective. Now, as I kept telling you at the very beginning of this lecture series, that to kind of ask some simple questions like even what is a prime number or what is unique factorization, and to say, well, we know the answer and here it is a little presumptive. All we can say is we know an answer. And it is one way of looking at it. And in mathematics, especially, more than perhaps in anything else, we look for a comprehensive manifold of perspectives. So we're not just looking for one way of looking at things. We're trying to look at things in many different ways. And in that way, we gain new knowledge by trying to do that. So Euler did just that with unique factorization theorem. He noticed that this theorem is equivalent to the analytic equation. So here's Euler. I like this. This is a nice painting. Euler is considered the most prolific of mathematicians in the history of the world. I think he's written more than Paul Erdős has. His volumes of writing are just totally gargantuan. So Euler discovered that if you take the product of the primes over the primes of this quantity 1 over 1 minus 1 over p to the s, now you recognize as a geometric series. And so when you write that out, you get product of over the primes of the sum of the 1 over p to the ks. And now, because you have this products of these power series, and when you multiply it out, you're going to get 1 over some n to the s, where n is going to be a product of prime powers, but you'll get it exactly once, and therefore it's summation 1 over n to the s. So this is basically the identity. This is another way of stating the unique factorization theorem. On the one hand, the right-hand side, you have 1 over n to the s, where n is going over all the natural numbers, but on the left-hand side, you have a product over the primes. So this tells us that every natural number can be written as a product of prime powers uniquely. So this is Euler's understanding of the unique factorization theorem. And because the harmonic series diverges at s equals 1, Euler concludes that there are infinitely many primes, because if there were only finitely many primes, the left-hand side converges as s goes to 1. But the right-hand side diverges as s goes to 1. Therefore, there are infinitely many primes. Now, this might sound like a trivial observation. It may also sound like a more complicated way of proving infinitude of primes. But the fact of the matter is, this so-called complicated way or analytic way of proving infinitude of primes is really at the heart of Dirichlet's theorem of the infinitude of primes in arithmetic progressions. Anuradha, you have a question?
Yes. Sir, could you please repeat what you said, what happens at s is equal to 1? Could you just say that sentence?
Sure. Thank you. Yeah. So if we look at this equation, at s equals 1, the right-hand side is summation 1 over n. And we all teach our first-year calculus students that summation 1 over n diverges. You compare it with the integral dx over x, and by the integral test, summation 1 over n diverges. And but at SE, if there were only finitely many primes, the left-hand side, which is a product, which would be a product over finitely many primes, would converge. And therefore, this contradiction proves that there must be infinitely many primes. That was Euler's proof. So we may say Euler gave a more complicated proof of something that Euclid did. Euclid showed that there were infinitely many primes also, but the proof of Euler's turns out to be the better one in the sense that it generalizes. So we should never scoff. We should never scoff at new proofs of old theorems. New proofs of old theorems may lead to new knowledge. So we have to be very cautious about that. I'm just trying to point to you did allude to the fact that I was going to say a few things about the philosophy of mathematics. Well, this is one of them. This is the idea that research, we don't know how research is done. We don't know how new ideas are discovered, but certainly by being open to new ideas, by being open to new perspectives, we can certainly make it better and easier for us to make these research. So Euler studied the zeta function as a function of a real variable. But later, Riemann derived its analytic continuation and stressed that deeper knowledge of prime numbers arises through the study of zeta as a function of a complex variable. So here we are in the realm of real numbers, and then we have the realm of complex numbers. And so somehow, all of a sudden, we're pushing our realm of awareness from natural numbers to rational numbers to real numbers to complex numbers. And this was the 18th century worldview of mathematics. Now, Euler was very successful in his study of the zeta function, and he was very successful in evaluating zeta 2k. The famous Basel problem asked for the evaluation of zeta 2 and was solved by Euler in an ingenious way. In 1734, Euler discovered this really beautiful formula, summation 1 over n squared equals pi squared over 6. Now, before dismissing this as a known fact, I think anybody who wants to call them a mathematician should look at that, a beautiful formula here, such a simple thing on the left-hand side, and it's connected with pi. And to find this, it took mathematicians quite a while. And more generally, Euler discovered that for zeta 2k, you can write down summation 1 over n to the k, when k is actually over all the integers. It turns out to be 2 pi I to the power k, b sub k over k factorial. So here the Bernoulli numbers show up again. The dash on the summation on the left-hand side means we omit n equals 0. And if k is odd, you see minus n to the power k and n to the power k cancel. So there's nothing. You get nothing from this formula. But for k is even, you get a beautiful formula. This is what Euler discovered. And for even k, we get a very beautiful formula involving the Bernoulli numbers. So there again, now, even though the Bernoulli numbers were introduced earlier as the coefficients of the polynomial that describes the sum of the kth powers of the first n minus 1 numbers, the Bernoulli numbers show up again when you're trying to look at summation 1 over n to the k, not summation n to the k, but summation 1 over n to the k. They show up again. I think this is fascinating. Now, the irrationality of zeta 3 was proved by Roger Appert in 1977, and now we know that infinitely many of the zeta 2k plus 1 are irrational. So the zeta function at the odd values, they're still mysterious. We really don't know what they are. We don't know whether any of these numbers are transcendental. We know pi is transcendental, and therefore for k even zeta k is going to be a transcendental number. We know that now. Because pi is transcendental. But do we know this at zeta 3 or zeta 5 or zeta 7 and so on? Those values seem to be extremely mysterious. So here, youngsters might be in the room, future Ramanujans hopefully attending this lecture. This is an interesting problem. And actually, Ramanujan himself had many things to say about the zeta function at odd arguments. Now, let me just give you a lightning proof of Euler's theorem, very short proof, based on the ideas discussed so far. technically his proof, Euler's proof, was not completely rigorous, but he had the right idea. His intuition is based on the idea that a polynomial is completely determined by its roots. Now, notice that I use the word intuition. Intuition is a very important factor in research, certainly an important factor in the life of any scientist, maybe human being in general. What is intuition? Well, it's hard to define, actually, but it is the function of reasoning, knowledge, and something else. So this something else is kind of a leap of the imagination. So his leap of the imagination in this case is that maybe I can treat the function sine pi t as if it is a polynomial in t with roots at all the integers. So you see, when is sine pi t equal to 0? Well, we know that sine of 0 is 0, sine of pi is 0, sine of minus pi is 0, sine of 2 pi is 0, sine of minus 2 pi is 0, so on and so forth. So we can see that all the roots of the polynomial sine pi t are all the integers. So he tried to say, well, let's get rid of t equals 0 by factoring out the t equals 0 part. Sine pi t is equal to pi t, and times product 1 minus t squared over n squared. This is what he actually proves. He proves this. He doesn't actually give a rigorous proof, but the intuition is correct. And so now you take logs and differentiate. Take logarithmic derivatives of both sides and differentiate. So you see, Euler was a master of using generating function. So just as I tried to tell you about the generating function of the sum of the kth powers of the natural numbers, similarly, you now can consider the sum of the generating function of summation of 1 over n to the k, somehow n to 2k, and you notice that, hey, we can actually find out what this is from this particular formula, that when I differentiate, take logs and differentiate, I end up getting pi t cos pi t over sine pi t equal to the series. On the one hand, the left-hand side can be rewritten in terms of our exponential function. Remember from your high school days that cos x is equal to either the ix plus either minus ix divided by 2, and sine x is equal to either the ix minus either minus ix divided by 2i. So using those formulas, you can now rewrite your left-hand side in terms of the exponential function, and then simplify it a little bit, and lo and behold, we're starting to see the Bernoulli numbers again. And indeed, that is the case. You write down in terms of your Bernoulli things, and now we compare coefficients from this particular formula here, and then compare it with that particular formula over there, and lo and behold, you end up getting a formula for zeta 2k in terms of Bernoulli numbers and pi to the k. So very remarkable formula here. Okay, now Euler studied, actually he introduced what's called a gamma function, fundamental paper written in 1729. Euler derived the analytic continuation functional equation for the gamma function. Now notice by the way, that Euler's work on the one hand with the zeta function, and then Euler was working with the gamma function. Perhaps in Euler's mind, these two seem to be two different functions, not apparently connected with each other. And so I always, coming back to Anuradha's assertion that somehow I'm interested in philosophy, Indian philosophy, and mathematics, philosophy of research, philosophy of knowledge, epistemology, and so on and so forth, I'm always intrigued by the fact that a person can be making discoveries independently at two different intervals of time without knowing or realizing that perhaps these things are connected. Somehow, we seem to only have awareness of a certain limited sphere of consciousness where ideas and grand ideas and inspirations are moving in a larger realm. And if we could only figure out how to catch these larger things, but at least if we're faithful to writing down what it is that does fall into our lap, instead of dismissing it, the goddess of knowledge will give us more knowledge to discover. So in that context, Euler was very enamored by the gamma function. The gamma function he defined as the integral from 0 to infinity e to the minus t to the s minus 1 dt. And the integration by parts shows that gamma s plus 1 equals s times gamma of s. And if you see for natural numbers, gamma of n plus 1 turns out to be n factorial. So here you have a sequence of the factorials. And somehow the gamma function, which is the integral, at natural numbers, it's a factorial function, but it actually makes sense for all complex numbers. Now, this is something Euler discovered. So he discovered perhaps that you should look at functions of complex variables. But what he didn't see was that you should think of the zeta function as also a function of complex variable. But he certainly discussed the gamma function. He showed that using this, you can see that gamma of s here originally makes sense for real part s bigger than 0. And this equation, which you got by integration by parts, allows you to rewrite gamma of s as gamma of s plus 1 over s. So now, this function, which originally defined for real part of s bigger than 0, now with this equation, it makes sense for real part s bigger than minus 1, because if I have a number which has real part s bigger than minus 1, when I add it, the real part is bigger than 0. So you get something that's known here. So in this way, we can step by step continue. So again, we have gamma s plus 2 is ss plus 1 gamma s. And so gamma of s is gamma s plus 2 divided by s times s times s plus 1, and the right-hand side is analytic. So inductively, we can continue the gamma function to the entire complex plane, and you can see it extends to a meromorphic function and poles with simple poles at s equals 0, minus 1, minus 2, and so on and so forth. Now, this is an interesting feature of mathematics. Number theory, which you may say is about natural numbers, and you're trying to understand the building blocks of natural numbers, inevitably leads you into these other worlds, the world of real numbers, the world of complex numbers, whether you like it or not. And in order to understand natural numbers, you have to kind of understand the real numbers and the complex numbers. So now we come to the episode of Riemann and the zeta function. In a fundamental paper of 1859, Riemann derived the analytic continuous functional equation for the zeta function, similar to what Euler was doing with the gamma function, but it took another 100 years to get to this kind of stage. So Riemann begins with the gamma function, and if you change some variables, and you can rewrite gamma s over 2 n to the minus s as the integral from 0 to infinity e to the minus n squared x to the s over 2 dx over x. And if you change x to pi x and the integral sum over the n's, we have this particular formula. So this is the starting point of Riemann. Pi to the minus s over 2 gamma s over 2 zeta s is the integral 0 to infinity x to the s over 2 of this function, summation n equals 1 to infinity e to the minus n squared pi x dx over x. So this is something similar to what Euler was doing with the gamma function. Somehow he does it with this zeta function. And this particular function that he's integrating here is really what's called a Jacobi theta function, which satisfies the functional equation. And Riemann showed that, so if you now fudge this, call it c of s, 1/2 s times s minus 1, pi to the minus s over 2 gamma s over 2 zeta s, then this extends to an entire function, satisfies a functional equation, cs equal to c of 1 minus s. So I hope everyone understands the profundity of what has just taken place, starting from the zeta function, which has been defined using natural numbers, and you're trying to see this function extended to the complex plane. You end up writing it as a Mellin transform of the Jacobi theta function. And then because the Jacobi theta function has actually a functional equation, this comes from the theory of modular forms, so let's not go there right now. You end up getting this remarkable functional equation in the line of symmetry. And so now it's telling us that the zeta function at S is related to zeta function at 1 minus S. Now, somebody seems to have raised a hand. Radha, do you know who this person is?
Yes, somebody called Sachin. Is there a question?
Sir, what is that functional equation that you told Jacobi theta function satisfies?
Yeah, I didn't want to go into that because it will take me too far afield, but the function, let me go back then. This function essentially where the red arrow is indicated, that's called a theta function. And it turns out that theta of 1 over x is square root of x times theta of x. And that Jacobi found essentially by studying the heat, what's called the heat equation. And it comes from the theory of the Poisson summation formula. Yeah. So if you want to go deeply into this, you could look at my problems in analytic number theory book, where the complete proofs are given. I hope that answers the question for now. There was another question. Yeah. Was there another question?
No, I don't think so.
Okay, great. Okay. Yeah, please feel free to ask questions, especially if it's an urgent question. That means it can't wait till the end. If it help you in understanding the slide, please do feel free to do that. Now we have established a functional equation between zeta s and zeta 1 minus s. And therefore, because we had proved this formula, zeta 2k is related to pi to the 2k times this Bernoulli number, it begs the question, what does this mean? In view of functional equation of for the Riemann zeta function, Euler's formula can be written in a simpler way, namely zeta 1 minus k is minus bk over k. Isn't that beautiful? I mean, of course, the zeta 2k formula was very nice, but zeta 1 minus k. Now, interestingly enough, this is true for every k, including when k is odd. When k is odd, bk we decided was 0. Therefore, the zeta function, as analytically continued by Riemann, has trivial zeros at all the negative even integers. So that's what you get. It's an interesting fact in its own right. And it is this formulation that will appear later in our discussion. This particular formula is what is the starting point of what is called P-adic L function theory. This particular formula, zeta 1 minus k. So if we suspend rigor, remember I talked to you about intuition. Ramanujan had a terrific amount of intuition, so did Euler. And I don't know, but intuition seems to be very much related to experimentation and a certain suspension of the rigor process. That's why sometimes physicists seem to have great intuition, because they're not very rigorous in their thinking, but they do stumble on really profound ideas in their own way. So if we suspend rigor for a moment, there's an amusing way to derive the above formula without the functional equation by the generating function method. So let's just say I want to understand what zeta minus k looks like, and I put down a power series. Okay, so summation k equals 0 to infinity zeta minus k to the k over k factorial, and then I'm sloppy. Of course, when you say zeta minus k, you do not mean summation n to the k. You mean the Riemann zeta function analytically continued. But let's be sloppy and just put summation n to the k and going from 1 to infinity. Of course, this term here doesn't make any sense because this whole silly thing diverges. But let's just not worry about that. And then interchange summation, just like we did at the beginning. You get a geometric series, and then sum it. Again, you get a geometric series, all right, but it better converge. But let's not worry about that. You get e to the t over 1 minus e to the t, and then rewriting this as minus 1 over e to the t minus 1. We can use our Bernoulli numbers, and we can now see that. Remember, we had the generating function for the Bernoulli numbers. Therefore, we can now write zeta minus k and compare the coefficient here, and lo and behold, we get this. Now, this is something that Ramanujan used to do very often. And in this way, he actually got right answers. And when things like this happen, you should ask yourself, perhaps there's a theory that you can use in order to get the right answer and justify the steps. And in this case, too, this argument can be made rigorous. And I did this some time ago with my former student, Marilyn Reese, and the paper is available on my website for anyone who would like to understand this. Yes, somebody has a question. Anuradha?
Okay, so my question is, here you just say that you introduce a series that diverges and you just interchange the summation. We know that we don't just interchange summations like that, right? Like if
No, we don't. We don't. Yeah, that's why I said there's not rigorous.
So why did we decide to use that way then? If it's not something
I'm
rigorous?
Yeah, because in order to say that the answer makes sense, or at least guess at an answer, you can sometimes suspend rigor to try to guess an answer.
Okay.
I see that. Yeah, so this is the aspect of what is called intuition. Yeah. So hopefully there are no undergraduates attending this lecture. All right. Let's now revisit prime numbers. At the beginning of this lecture, we defined a prime number as a natural number having no non-trivial factorization. Now we want to take another perspective which shapes our modern view of number theory. So we're all familiar with the usual absolute value function defined on the rational number field. Usual absolute, you take what is the absolute value of -2? 2. What's the absolute value of 2? 2. And so on and so forth. So we know the absolute value function. It satisfies 3 properties. The absolute value is always non-negative, except for it's 0 if and only if x is 0. And the absolute value function is kind of multiplicative. Absolute value of xy is the absolute value of x times the absolute value of y. And finally, absolute value of x plus y is less than or equal to absolute value of x plus the absolute value of y. Okay, so you have the triangle inequality. And so this motivates the following definition. Suppose we have a field F. A norm on a field F is a mapping of the field into the non-negative real numbers such that the norm of x is 0 if and only if x is 0. The norm of xy equals the norm of x times the norm of y. And the norm of x plus y is less than or equal to norm x plus norm y. This is a triangle inequality. Okay. And we can always define what's called the trivial norm. The trivial norm would be just to set the absolute value of 0 to be 0 and the absolute value of anything else to be just simply 1. And you can see that that silly thing will satisfy these 3 properties. And this is what's called the trivial norm. And we'll just discard this silly trivial norm. And we'll always talk about non-trivial norms. And notice also in a field when 0 is not the same as 1, that means the additive identity should not coincide with the multiplicative identity. We have that the absolute value of 1 is always 1. And so the absolute value of -1 squared is 1. So the absolute value of -1 is also 1. And therefore, this absolute value function or the norm map is symmetric. So with this said, we will show that each prime number will give rise to a norm on Q. So we know about the usual absolute value, but I now want to talk about this norm function, and I want to show you that the usual absolute value is certainly a norm, but there are infinitely many norms we can construct on the rational numbers. And so this is how we do it. It's called a P-adic norm. So let's take a prime number P, and for each non-zero rational number x, we can write it by the unique factorization theorem as p to the vp of x times x1, where x1 has nothing to do with p. That is, it's a rational number co-prime to p when x1 is written in lowest term, both numerator and the denominator are co-prime to p. So what am I doing here? I'm taking a rational number x and writing it as a over b. A and b are natural numbers. And let me just get some water. Yeah, so you take a rational number x and write it as a over b, a and b natural numbers. You factor a and b using unique factorization theorem. And then you pull out the power of p. There could be nothing there. There could be 0 power of p. But whatever it is, there's going to be p to some vp of x, and vp of x is going to be an integer. And we're going to be defining the p-adic absolute value of x as p to the minus vp of x. That's our definition. You may ask, why do you do that? Well, I'll tell you why. It satisfies these properties. It satisfies the property for x equals 0. We'll just set the thing to be 0. It's easily checked that this is a norm. And in fact, the last inequality, which is called the triangle inequality, is satisfied in the sharper form that the absolute value of x plus y, the p-adic absolute value of x plus y, is less than or equal to the maximum of the two p-adic absolute values. And I'm going to leave these as exercises for you to do. So with this particular metric, the sequence, the powers of p to the n with n equals 1, 2, 3 converges to 0. So in the ordinary absolute powers of p go to infinity. But in the p-adic metric, this converges to 0 because so the larger the power of p that appears, the closer it is to 0. In this way, we get a norm for each prime p. So from a norm, we can get a distance function, metric. Given a norm, we can define a distance between x and y. It's the norm of x minus y. This makes the field into a metric space. And you may have studied some topology. And so with the idea of a metric, you have open sets and you can have a topology. And we say two metrics, D1 and D2, are equivalent if they induce the same topology on F. Two norms are equivalent if they induced metrics are equivalent. So we could always modify the metric, but if it's the same, convergence is the same in both metrics, we call them equivalent. So if I take a number now, number C between 0 and 1 and p is a prime, I can also define another metric using this metric, the absolute value of x to be c to the vp of x. And this particular norm is equivalent to the p-adic norm that I just defined earlier. So now we have the following celebrated theorem of Ostrowski, which says that up to equivalence, the only norms on Q are the p-adic norms or the usual norm given by absolute value. So here now we understand prime numbers in a different way. Each prime number is giving rise to a norm on the rational numbers. And the only norm you can create on the rational numbers is either the p-adic norm or the usual absolute value. So this gives us a new insight into what is a prime number. So let me this theorem gives us an important perspective into the notion of a prime. So let me give you a quick proof of Ostrowski's theorem, because Ostrowski's theorem is considered the turning point of 20th century number theory. Yes, somebody has a question.
Yes, my question is, previously you just mentioned that if you have a field and you have a norm on a field, then you can define the distance or the metric on that field as the distance between 2 points and y is the difference, like the norm between x minus y, right?
Yeah.
So my question is, what's the interpretation of defining that p-adic norm? Like what's its interpretation? Does it have an interpretation?
Absolutely, it has an interpretation. So as I mentioned at the very beginning, the p-adic norm is measuring to what power of p enters the number. So it's keeping track of the power of p. So if there are larger and larger powers of p in the number, that number will be declared to be very close to 0. That's basically what's happening. Okay, I hope that. So it's so each p-adic norm will now try to keep track of powers of p's that are floating around in each part. So that's what's going on. So we have a 2-adic norm, we have a 3-adic norm, we have a 5-adic norm, we have a 7-adic norm. And as you will see from the proof, these norms can only arise from primes. So here's the proof of Ostrowski's theorem. Here's Ostrowski. lived to a pretty long time. Following theorem changed the course of 20th century number theory, and surprisingly, it is easy to prove it uses nothing more than the Euclidean algorithm. That's why I went to the trouble of proving the Euclidean algorithm. Yes, somebody had a question? The admin had a question? No.
No.
Oh, okay.
I think it was by mistake.
Oh, okay. So here's Ostrowski's theorem, 1918. Every non-trivial norm on the rational numbers is either a p-adic norm or the usual absolute. Yes.
On Rn, we have infinity norm and p norms. Infinity norm is just limit of p norms as p tends to infinity. Is there modulus norm on the rational numbers? Is it a limit of p-adic norms?
On Rn, what do you mean Rn? You mean n copies of the reals?
On Rn, p norm is defined like this: summation mod xn raised to p raised to 1 by p.
Yes, he means n copies, n tuples of overall.
N tuples of real numbers, and
Yes.
sup norm is defined like maximum of mod xn's.
Okay. I will not discuss the n-dimensional case right now. That it will be relegated.
But here on rationals, we have p-adic norms and modulus also.
Yes.
So what is the relation between modulus norm and this family of p-adic norms? Is there a limiting?
Yeah, there's absolutely. There's what's called the product formula. I'll come to that at the very end. You're too excited and now jumping the gun and trying to understand everything all at once. We will come there. Yes, absolutely. These norms are all related.
Okay.
And they're connected. What's called the product formula will show up later on.
Okay, thank you.
Yeah. So let us focus now. Just fix our attention only on the rational numbers for the moment. And so what are the possible norms you can create? There's only the p-adic norms, one for each prime p, or the usual absolute value. So let's just try to prove this. So we begin. Suppose that the norm of all the natural numbers is less than or equal to 1 for all integers n. So that's case number 1. Case number 2 will be there is an n where the absolute value of n or the norm of n is bigger than 1. So in this case, since the norm is non-trivial, there is an n such that the absolute value of n, norm of n, is strictly less than 1. And because the norm of minus n is the same as norm of n, we can assume without any loss of generality that n is positive. And then amongst all these numbers, natural numbers, whose norm is strictly less than 1, let n naught be the least such, then n naught must be a prime number because, again, if it's not a prime number, because that multiplicative property, remember the norm of ab is equal to norm of a times norm of b, the multiplicative property says it has to be a prime. And now, so n naught is a prime. Now, if take q, which is not equal to p, we claim that the norm of q is going to be 1. If not, the norm of q has got to be less than 1. And for sufficiently large q, the norm of q to the n is going to be strictly less than a half. Similarly, for sufficiently large m, the norm of p to the m is going to be strictly less than a half, p being the prime that you had earlier. And since p to the m and q to the n are co-prime, we can find integers x and y so that u times p to the m plus v times q to the n is equal to 1. And now take norms. Norm of 1 is 1. We agreed on that. And then use the triangle inequality, and lo and behold, you end up getting 1/2 plus 1/2, which is less than 1. It's a contradiction. And therefore, the norm of q for any other prime q has to be 1. It's amazing. Therefore, there's only one prime actually running the show here. Once you have a norm, it had to come from a prime. And that's it. This is it. And now you define take that norm of the prime and then define your n, the norm of n, to be c to the vp of n. And that's your p-adic norm, which is, remember I said, equivalent to the p-adic norm that I defined earlier. So this is how you get the p. Now that's the case 1. Case 2 is what we'll do in the next slide. Suppose there's a natural number n such that the norm of n is bigger than 1. Let n naught again be the least, again using the well-ordering principle, and write your absolute value of n naught or norm of n naught to be n naught to the alpha, and for some alpha. So somebody raised a hand? Oh, by accident, okay. And now every natural number can be written in terms of base n naught. N naught is, so we all know this from our high school days. Write n now in terms of the base a n naught. And notice that the AIs are now strictly less than n naught. This is again the division algorithm. We're using the division algorithm to write this. And because n naught was the least such, the absolute value of AI is less than equal to 1 by the definition, and by the triangle inequality, we get the absolute value of n is less than or equal to the absolute value of the summands, and then it's less than or equal to 1 plus n0 alpha plus n0 alpha to the s, and then because n0 is at least 2, we get a constant which converges, and then we get this inequality that the absolute value of n is less than or equal to n naught to the alpha s by the choice of n naught with c a constant independent of n naught. And then since from here, notice from here, n is bigger than n naught to the s. So we deduce for all natural numbers n that c, the absolute value of n, or the norm of n, is less than or equal to c times n to the alpha, and for some absolute constant c. And then again, playing this trick with taking powers, we see that the constant wouldn't change with taking powers, but then by taking the nth root, we end up getting this inequality. So we get rid of the constant by taking n going to infinity. And so we finally proved that the norm of n is less than or equal to n to the alpha for all natural numbers. And we can also deduce the reverse inequality, because n naught to the s plus 1 is bigger than n naught to the s. We have an inequality in the following sense, that the norm of n naught to the s plus 1 is equal to this particular norm. Use the triangle inequality, and we end up getting that the norm of n is again bigger than n naught to the s plus 1 alpha minus n naught to the s plus 1 minus n to the power alpha. And then doing the obvious inequalities, you end up getting c1 to the n to the alpha. Again, the same trick of taking capital nth powers of n allows you to eliminate the constant. And then this way you end up getting that the absolute value of n is, the norm of n is actually n to the alpha. Now, this norm is equivalent to the usual absolute value. So in the second case, you're not getting anything new. In the first case, you're getting all the p-adic norms. In the second case, you're not getting anything new. It's the usual absolute value. This proof, this is high school stuff. This is high school stuff, and yet it was discovered as late as 1918, and it changed the fate of 20th century. Now, we know that in a metric space you can consider Cauchy sequences, and so these are sequences xn with the property that for any epsilon positive, there's a capital N, such that xn minus xm is less than epsilon. It gets closer and closer for sufficiently large. So given a field f with a norm, if you take all the Cauchy sequences with respect to that particular norm, you can define addition and multiplication on those sequences pointwise by just setting, component-wise addition, component-wise multiplication. And this turns out to be a commutative ring. And the subset of those sequences consisting of null Cauchy sequences which converge to 0, that turns out to be a maximal ideal. And if you know your basic algebra, if you have a commutative ring, and a maximal ideal M, the quotient is a field. And indeed, so you can now take your rational numbers, you can consider all the Cauchy sequences with respect to your norm function, and then you can complete that and you get a new field with this trick. So in this way, for the rational numbers, you take the usual absolute value. When you complete it, you get the field of real numbers. But now that we have these p-adic norms, if we take the p-adic norm and complete the rational numbers with respect to the p-adic norm, we get a new field called the field of p-adic numbers. So all our life, we've only been dealing with the real numbers when there's a whole family, an infinite family of fields that we really should be looking at. We've been missing out on that. The real numbers is a complete field. When you take the rational numbers with the usual absolute value completed with respect to this norm, we get a field of real numbers. But now when we take the rational numbers with the p-adic absolute value and complete it with respect to this p-adic norm, we get the field of p-adic numbers. one for each prime P. Thus, the field of rational numbers can be seen as a subfield of a p-adic numbers for each prime P. And from this perspective, it is convenient to view the usual absolute values as an infinite prime. So now we've changed our perspective. Primes and norms kind of go together. For each prime P, we produced a norm. And therefore, there must be a prime that corresponds to the usual absolute. We just call that the infinite prime. And the real number field is the completion with respect to this infinite prime. This viewpoint is called the adelic perspective. So somehow you should treat all of these things as the same. We can extend the norm that we define on the rational numbers to this completed field in the kind of obvious way. I'm just going to flash this. By the way, I'm going to give maybe Anuradha the slides, and she can post them to this registered participants so that they can have this lecture in the form of slides as well. I can supply you with the slides.
I will.
Yeah. So if I'm going a bit too fast, it's because it's pretty routine. Also, I'm running out of time. Pretty routine, and I'm sure the students can check these things. So we define the norm on QP using the Cauchy sequences because QP was constructed using Cauchy sequences, and it turns out that this turned it into a norm. Okay. Now, so we leave the details as an exercise. So this is a kind of a little hands-on kind of exercise that students may want to do after the lecture. In this field of p-adic numbers, there's a subring called the ring of p-adic integers. Those are the things that have p-adic norm less than or equal to 1. And in this case, the set of all p-adic integers whose norm is strictly less than 1 is a maximal ideal. And every element of x of m satisfied VP of x is at least 1. So we deduce that m must be p times zp. Every non-trivial ideal of zp is a power of m. And so we have what's called an example of a local ring. A local ring is a commutative ring with only one maximal ideal. These are called local rings. And this is an example, typical example of that. And the ordinary integers form a dense subset of ZP. And this can be, again, proved just simply by Chinese remainder theorem. Given an x, we want to find p-adic integers close to the to the thing by approximating it. So we finally find that you can do that. You can find a p-adic integer sufficiently close to a p-adic rational number. And this leads us to what are called p-adic expansions. So Z is dense in ZP, and we can find that every element in ZP can be thought of as a formal power series in P. And so this goes back to the very first slide that I tried to talk about of expanding functions, meromorphic functions as a Laurent series. We now figured out what you can do in the context of the p-adic numbers. So in the context of p-adic numbers, these elements of QP also can have a formal series of this type. And you have to understand that this series, the convergence, is with the p-adic norm. And ZP is a locally compact space, topological space. And what does locally compact means? Every point has a compact neighborhood. That's what locally compact means. Compact locally. Every point has a compact neighborhood. And then again, to try and see this is an application of the Chinese remainder theorem, or the fact that everything can be written as these residue classes. And so this is analogous to the Laurent expansion of meromorphic functions mentioned in the beginning. So it's useful to observe the analogy with the Laurent series in the field of meromorphic functions of a complex variable. At each point z, a meromorphic function has a Laurent expansion which is unique. This suggests that a rational number is denominator divisible by p. We can think of it as a p-adic number having a pole at p. And this analogy has been a guiding force for much of the development of p-adic analytic number theory. So infinite series in the p-adic metric, if you can consider the convergence of p-adic infinite series, you get some very interesting series. A series converges in the usual absolute value, then the nth term tends to 0, but the converse is not true because the harmonic series is an example, right? But in the p-adic world, the converse is true. And maybe, I think your head of department was saying it's a pity that we don't teach p-adic numbers to first year undergraduates. I think it's because of this theorem, the danger of this theorem being misunderstood. But first, I think we should understand the real topology carefully before we try to understand the p-adic topology. So here, p-adic series summation Cn converges if and only if the nth term goes to 0. So it's kind of very convenient and neat. And the proof is very simple. You just look at the axioms, triangle inequality, and it turns out the proof is actually quite easy to show. And this theorem gives rise to some interesting examples. So here's some simple examples or exercises. So summation p to the n now converges. What does it converge to? It converges to, what do you think it is? If you treat it as a geometric series, it'll be 1 over 1 minus p, right? The series summation n factorial converges, but it's still unknown if this number is a p-adic irrational. Because n factorial has higher and higher powers of p, and therefore it goes to 0. Therefore, the series converges. Now, here's another interesting one. Summation n times n factorial equals -1. And you may say, oh, wait a minute, how could it come to a negative number? The idea of a negative number is only in the real world, okay? In the p-adic world, this negative and positive doesn't really make sense. Now, how do you prove this? Well, if you, by induction, I'll leave this as an exercise, you can prove summation n times n factorial turns out to be n plus 1 factorial minus 1. I mean, you can see the partial sums are converging to -1. So taking p-adic limits gives the result. So you can have interesting, what we can call fun with infinite series, especially with these p-adic series. So each QP is a new window. Field of real numbers is only one completion of Q, but we have infinitely many completions of Q with respect to each of these p-adic norms. Each QP offers a different completion, one for each prime P. It seems as if we're looking at the world through only one color, monochromatic view of life all this time, when there were infinitely many colors and infinitely many perspectives. So we've been looking at the world through only one color, but there are infinitely many colors. Okay, so I hope I've convinced you now that one life runs through all, like a continuous chain of which all these various forms represent the links, link after link, extending almost infinitely, but of the same one chain. So we have to look at the totality, but each of these is a different world. And so there's a nice quotation of Vivekananda, which is very appropriate to describing the world, the idyllic perspective. So thank you very much for your attention. And as is customary after a talk, everyone has tea. So I invite you to my tea stall. Thank you. I did not Photoshop this. That's actually a picture.
Yes, let us thank the speaker. Very nice talk. I think in this short span of 1 hour, starting from prime numbers, we have traveled a lot, and introduction to the p-adic numbers to some extent we have had. I think in different ways we will be able to see these p-adic numbers in the next lectures. But various things that we learned today, starting from Aryabhata's starting work about sum of kth powers of first n natural numbers. Now this was done by Aryabhata for k equal to 1, 2, and 3, as was mentioned by Professor Ramamurthy, and it was generalized later by Bernoulli, and these things are going to be useful in the later lectures. That is why he has mentioned these things, but these are all very important things that the students should know. I would like to just mention similar thing in the work of Aryabhata. That is, Aryabhata actually at the beginning he gave methods for finding square roots and cube roots of integers. And the method, if we see the method, we see that he knows how to find the nth root also, because at that time the binomial theorem is not stated in the way in which we know, but the method that first you subtract a square, then you subtract 2 times a times b, all that method tells us that we can in the same way find out the nth roots of integers, and moreover we can find out the nth roots correct to any number of places of decimal. That also is very much visible from the method of Aryabhatta. And similarly, because Aryabhatta only states the results and it is not clear how he has obtained, but these answers themselves tell that he must be knowing much more than what he has written in his books. So that's a good information that Professor Ramamurthy has given to us, and it was a very interesting talk. Many things were covered. I think we have done it very fast, but if we do not do it, then it will not be possible to deal with the important topics which will be done in the remaining 4 lectures. So probably the participants, at least the students, they should refer to some books also, so that they can revise these concepts and they should be more prepared for the later lectures. So I think if there are any questions or queries, the participants are most welcome for that. Yes, I think Sripad had something to say.
Yes, I have a question.
Yeah,
Am
go
I
ahead.
audible? Yeah.
Yep.
Okay. So when we complete Q with the usual norm, we get real numbers, and there is a nice geometric way to see the real line. Is there such a geometric description of QP?
Yeah, that's a good question, and the answer is no. Yeah, it's interesting, isn't it? We are visual creatures, but many of these abstract ideas don't have very good visual representation. There are some ways of thinking of it. We just think of it as these infinite P-adic series. That's basically just like Laurent expansions, that's about the only way I think, just as we think of real numbers as decimal expansions, we can think of a decimal expansion as a real number. In that way, I think that's about the only, but visualizing as points on a line, no, I think in some sense it could be detrimental to carry that kind of imagery to the P-adic world. It just doesn't work.
You may perhaps later prove that QP is contained in complex numbers in some way.
Not really. Those complex numbers are not the same complex numbers. CP would be the algebraic closure of QP. And that is not the same as the complex numbers.
Okay.
Yep.
And second question, if I may ask, where is this Ramamurthy tea stall? Which place?
It looks like it's in Chennai somewhere. I don't know actually where it is, but yeah, it's in Chennai. Yeah.
Sure.
Thank you.
So next time we meet, maybe we could.
Yeah. We should definitely try it out. Yes.
Well, there is a simple question from my side.
Yeah. Yeah.
So as we know that the QP and with the P-adic norm, now we define that. Is it the complete with respect to that norm?
Yeah, that's what it is. Yeah. So what you yes, it's complete with respect to that. That's correct. That I didn't kind of prove, but that can be done. And that was all those slides at the very end. That was
now this will be the one of the very good example to my students, because we have the function analysis course at the third semester, and we are talking about the numbers. Now this is the new example that we got now, the QP space with the P-adic norm, and now definitely we can talk about the completeness of it.
Yeah, QP is complete, exactly. Yeah.
Okay, and further, it's okay. Means next lecture we can talk about the completeness and other things.
Yeah. Yeah, next lecture we'll talk about more details of this.
Okay, so the nice thing that you presented, we will listen the new things now, the periodic norms and all these things. As I'm doing the work in partial differential equation and all these things, so this is definitely the new to me. But one interesting thing, I come to the conclusion here. Interesting, I noticed it will be the periodic norm and expansions of these zeta functions regarding with the periodic will be the useful to me, special function, because of one of my students is working on the special functions, that is Lie algebra extensions of some generating functions. So with this one, as we have the collaborations with H.M. Srivastava, and with the in that space we define about that is the special functions, and we extend the external functions to us. So in expansion of external functions, we need this kind of the expansion here. So definitely with these new ideas of the periodic this kind of the will be useful to us. Thanks.
You're welcome. Yeah.
Gangaram?
So if there are not more questions, I think Ramurthy sir would certainly like to have his breakfast now, and
Yeah.
I think all of us would like to have snacks. And I think over that, let us think about this lecture. As Katre sir has already said, though the lecture was of 1 hour, I think the content for study is much more. So we hope to meet you tomorrow after looking through
Just
the lectures.
Just tell me, Honorable Vice Chancellor Professor R.D. Kulkarni, he sent the message to us that he will be attend our valedictory lecture. That is lecture on 1st of September. He will attend. He will provide the time. He give the commitment that he will attend the lecture on 1st of September. Okay.
So thank you very much, sir, and see you tomorrow. So I will circulate the link. So one announcement for all the participants: the lecture link for tomorrow is going to be different from what was circulated today. So please join on the new link which will be sent. And sir, you will send me the slides, I suppose, and then I will circulate.
Yeah, I'll send the slide. Yeah, absolutely.
Okay. Thank you very much.
Thank you, sir. Thank you, Katre sir. Thank you, Sripat sir. Now I think we'll end the session.
Yeah, thank you.
And
Bye.
thank you to all the faculty members from other universities also who have joined. And thank you to all the participants. See you tomorrow.
Thank you, sir.
Yeah, goodbye. Bye.
Bye.